Hello everyone. We invite you to listen to interesting scientific facts that will help you fall asleep gently and at the same time learn something new. Relax, close your eyes, and let a calm voice guide you into the world of knowledge and sweet sleep. Take a slow breath in and gently let it go. Tonight we are not traveling to distant galaxies. We are staying home, on Earth. The only world we know that holds oceans, forests, clouds, and life. Earth formed about 4.5 billion years ago from dust and gas orbiting a young sun. Tiny particles collided, stuck together, and slowly built something larger. Over millions of years, gravity shaped this growing mass into a sphere. That sphere is now your home. Earth is about 12,742 kilometers across. It may sound enormous, but compared to the Sun, it is small. Over 1 million Earths could fit inside the Sun. And yet, this modest planet is perfectly balanced. Earth orbits the Sun at about 30 kilometers per second. That is over 100,000 kilometers per hour. But you do not feel that speed. Everything around you is moving together. The motion is smooth, continuous, gentle. At the same time, Earth spins on its axis once every 24 hours. That steady rotation gives us day and night. Right now, somewhere on Earth, the sun is rising. Somewhere else, it is setting. Somewhere, rain is falling softly on leaves. Earth's atmosphere is thin, just a delicate layer of gases surrounding the planet. If Earth were the size of an apple, the atmosphere would be thinner than the apple's skin. And yet, that thin layer protects all life. It shields us from harmful radiation. It burns up small meteors before they reach the ground. It holds oxygen for animals and carbon dioxide for plants. The air you breathe has likely been breathed before. Oxygen molecules move constantly. Some may have once passed through ancient forests. Some may have been inhaled by dinosaurs millions of years ago. Nothing on Earth is truly separate. Water, too, is constantly moving. The water you drink may have once been part of a glacier, a cloud, or the ocean. Through evaporation and rain, Earth's water cycles endlessly. About 71% of Earth's surface is covered by oceans. These oceans regulate temperature, absorb carbon dioxide, and hold countless forms of life. Even the deepest parts of the ocean, nearly 11 kilometers below the surface, contain living creatures adapted to darkness and pressure. Earth's magnetic field quietly protects us. Deep inside the planet, the outer core is made of molten iron. As it moves, it creates a magnetic field that surrounds the Earth like an invisible shield. This field deflects charged particles from the Sun. Without it, life would be far more difficult. The continents slowly move. They drift only a few centimeters per year, but over millions of years, they reshape the planet. Mountains rise, oceans open and close. But the motion is slow, calm, patient. Earth also tilts slightly, about 23.5 degrees. That tilt gives us seasons. When one hemisphere leans toward the sun, it receives more sunlight. When it leans away, temperatures cool. This gentle tilt creates cycles of change: spring, summer, autumn, winter. The moon plays a quiet role as well. It stabilizes Earth's rotation. It creates tides in the oceans. It slows Earth's spin gradually over time. Without the moon, Earth would wobble more dramatically. Instead, we have steady rhythms: day and night, tides rising and falling, seasons turning. Earth is not perfectly still. It breathes in cycles. Carbon moves between air, oceans, plants, and soil. Rocks weather slowly. Volcanoes release gases. Forests grow. Leaves fall. Life adapts. And through all of it, the planet remains balanced. From space, astronauts describe Earth as peaceful, a blue sphere floating in darkness, thin clouds swirling over oceans, no borders visible, just one connected world. You are resting on that world right now, on a planet that spins, orbits, and flows through space with remarkable stability. Earth has existed for billions of years. It has survived asteroid impacts, ice ages, and volcanic eras. And tonight, it continues quietly on its path around the sun. The ground beneath you is solid. The atmosphere above you is protective. The oceans move in steady tides. The planet turns gently in the dark. Take one more slow breath. In and out. You are safely held on a world that has been stable for billions of years, and it continues turning softly beneath the stars. Take a slow breath in and gently let it go. Now let us turn our attention to something invisible yet constant. Gravity. You do not see it, you do not hear it, you do not feel it directly, and yet it holds you gently against the surface of the Earth. Gravity is not a force that pushes down. It is the natural attraction between objects with mass. Every object in the universe pulls on every other object. The reason you do not notice the pull of a chair or a tree is that Earth is massive. Its mass is about 5.97 sextillion kilograms. That is a number so large, it is difficult to imagine. Because Earth is so massive, its gravitational pull is strong enough to hold oceans in place, to keep the atmosphere from drifting into space, to anchor mountains, cities, forests, and seas. Gravity gives your body weight. On Earth's surface, gravity accelerates objects downward at about 9.8 meters per second squared. If you drop a leaf, a stone, or a feather in a vacuum, they fall at the same rate. Gravity does not prefer heavy objects. It treats all mass equally. But air resistance slows lighter objects, making the fall appear gentle. The moon experiences gravity too. Earth's gravity pulls on the moon. At the same time, the moon pulls back. This mutual attraction keeps the moon in orbit. If Earth suddenly had no gravity, the moon would drift away. The oceans would lift. The atmosphere would escape. But gravity is steady, reliable. It has been working quietly for billions of years. Gravity also shapes the planet itself. Because of gravity, Earth forms into a sphere. When a body becomes massive enough, gravity pulls equally from all directions, smoothing out irregular shapes. Small asteroids can be lumpy. Large planets become round. Earth is not a perfect sphere. It bulges slightly at the equator because it rotates. As Earth spins, centrifugal force gently pushes outward, making the equator slightly wider than the poles. But the difference is subtle. The planet remains beautifully balanced. Now imagine the oceans. Gravity pulls the water toward Earth's center, but the moon's gravity pulls gently on the oceans too. This creates tides. As Earth rotates, different parts of the planet pass through these tidal bulges. High tide, low tide, a slow breathing of the seas. Even the sun contributes to tides. When the sun, moon, and Earth align, tides become stronger. When they form right angles, tides become weaker. Gravity creates rhythms, cycles, patterns. The same gravity that keeps your feet on the ground also keeps Earth in orbit around the sun. Without gravity, Earth would fly off into space in a straight line. Instead, gravity bends its path into a gentle curve, a continuous fall around the sun. Orbit is simply falling forward while constantly missing. This balance has lasted for over 4 billion years. Gravity is not dramatic. It does not flash or roar. It does not announce itself. It simply holds, steady, constant. You are held by gravity right now, supported by the planet's mass, anchored to a world that spins at over 1,600 kilometers per hour at the equator. And yet, you feel still. That is the quiet miracle of gravity. It allows motion without chaos, speed without turbulence, change without collapse. Even your body depends on it. Your bones grow strong because gravity gently presses on them. Your muscles maintain tone because gravity resists them. Astronauts in orbit, free from Earth's gravity, must exercise daily to maintain strength. Gravity shapes life, yet it does so softly. There is no tension in it, only a quiet pull toward the center. Now take another slow breath, in and out. Imagine gravity as a gentle embrace, not heavy, not oppressive, just a constant presence keeping oceans in place, holding mountains steady, and anchoring you safely to the surface of a living world. The physics of gravity is simple in principle, yet profound in effect. It binds galaxies, it shapes stars, it forms planets. And tonight, it holds you calmly as Earth turns beneath the stars. The oceans and atmosphere of Earth operate as interconnected systems governed by physics, solar energy, gravity, and planetary rotation. Together, they create slow, repeating cycles that regulate temperature, distribute moisture, and sustain life. Approximately 71% of Earth's surface is covered by oceans. These vast bodies of water contain about 97% of all water on the planet. Because water absorbs and retains heat efficiently, the oceans function as a global temperature stabilizer. During the day, oceans absorb solar radiation. At night, they release stored heat gradually. This process moderates extreme temperature fluctuations between day and night and between seasons. Coastal regions, for example, experience milder climates than inland areas because of nearby oceanic influence. Ocean water is constantly in motion. Surface currents are primarily driven by wind patterns, which themselves are influenced by Earth's rotation and uneven solar heating. One of the most significant systems of ocean circulation is known as the global conveyor belt, or thermohaline circulation. Thermohaline circulation is driven by differences in water temperature and salinity. Cold, salty water is denser and sinks, while warmer water rises. In polar regions, surface water cools, increases in density, and sinks deep into the ocean. This movement sets off slow-moving currents that travel thousands of kilometers over centuries. These deep currents transport heat from equatorial regions toward the poles. Without this redistribution of thermal energy, Earth's climate would be far more extreme. On shorter timescales, tides represent another steady rhythm of the oceans. Tides are caused primarily by the gravitational pull of the Moon and, to a lesser extent, the Sun. As Earth rotates, different regions pass through tidal bulges, creating cycles of rising and falling sea levels. Most coastal areas experience 2 high tides and 2 low tides approximately every 24 hours and 50 minutes. This predictable motion influences marine ecosystems, coastal geology, and human activity. Above the oceans, the atmosphere forms another dynamic yet orderly system. The atmosphere consists mainly of nitrogen, about 78%, and oxygen, about 21%, with small amounts of argon, carbon dioxide, and trace gases. Although thin compared to the size of the planet, this layer is essential for regulating temperature and supporting life. Weather patterns arise from the uneven heating of Earth's surface. The equator receives more direct sunlight than the poles. Warm air near the equator rises, creating areas of lower pressure. Cooler air from higher latitudes moves in to replace it. This circulation forms large-scale wind patterns known as Hadley cells, Ferrel cells, and polar cells. Together, these systems distribute heat and moisture around the globe. Earth's rotation influences wind direction through the Coriolis effect. In the northern hemisphere, moving air deflects to the right. In the southern hemisphere, it deflects to the left. This deflection contributes to the formation of trade winds, jet streams, and large storm systems. Cloud formation is part of the hydrological cycle. Water evaporates from oceans, lakes, and soil. As warm air rises and cools, water vapor condenses into droplets, forming clouds. When droplets combine and grow heavy enough, precipitation falls as rain, snow, or hail. This cycle of evaporation, condensation, and precipitation continuously recycles fresh water. The same water molecules may move from ocean to cloud to river and back again over years or centuries. Storm systems, though sometimes intense, follow physical laws. Hurricanes, for example, draw energy from warm ocean water. They rotate due to the Coriolis effect and weaken when they move over land or cooler waters. Even large-scale climate patterns follow rhythms. The El Niño Southern Oscillation is a periodic warming and cooling of surface waters in the Pacific Ocean. It influences global weather patterns, shifting rainfall and temperature distributions every few years. Despite variability, Earth's climate system maintains long-term stability through feedback mechanisms. Clouds reflect sunlight. Oceans absorb carbon dioxide. Ice sheets reflect solar radiation. These interactions operate slowly and continuously. From space, meteorologists observe swirling cloud bands, rotating cyclones, and flowing ocean currents. Yet, beneath this complexity lies a balance shaped by gravity, rotation, and solar energy. The oceans rise and fall. Air warms and cools. Clouds form and dissolve. These movements may appear dynamic, but they are governed by steady physical principles. Earth's oceans and atmosphere function like a planetary heartbeat. Not fast, not chaotic, but rhythmic. Each tide, each breeze, each rainfall is part of a system that has operated for billions of years. The planet does not rush. Water circulates, winds flow. Heat moves from warm regions to cooler ones, and through these calm physical processes, Earth remains habitable. The slow rhythms of oceans and weather continue tonight, as they always have. Steady, measurable, and quietly sustaining life on a rotating world. Earth is not solid all the way through. Beneath its surface lies a layered internal structure shaped by heat, pressure, and gravity over billions of years. Scientists understand Earth's interior primarily through the study of seismic waves generated by earthquakes. As these waves travel through the planet, their speed and direction change depending on the material they pass through. By measuring these changes, geophysicists have mapped the internal layers of Earth. Earth is composed of 4 main layers: the crust, the mantle, the outer core, and the inner core. The crust is the outermost layer. It is the thin shell on which continents, oceans, mountains, and ecosystems exist. The crust varies in thickness. Under oceans, it averages about 5 to 10 kilometers thick. Under continents, it can reach 30 to 70 kilometers. Compared to Earth's total radius of about 6,371 kilometers, the crust is extremely thin. If Earth were the size of an apple, the crust would be thinner than the apple's skin. Beneath the crust lies the mantle, which extends to a depth of approximately 2,900 kilometers. The mantle makes up about 84% of Earth's volume. It is composed primarily of silicate rocks, rich in magnesium and iron. Although the mantle is solid, it behaves plastically over long periods of time. This means it can slowly flow under pressure. Heat from deeper layers causes convection currents within the mantle. Hot material rises, cools, and then sinks again. These convection currents drive plate tectonics. Earth's crust is divided into large pieces called tectonic plates. These plates float on the semi-fluid upper mantle. They move slowly, typically a few centimeters per year. Over millions of years, this motion reshapes continents and ocean basins. When plates collide, mountains form. When they pull apart, new crust emerges at mid-ocean ridges. When one plate slides beneath another, earthquakes and volcanic activity occur. Despite these dramatic events, plate motion is gradual. The continents drift slowly, almost imperceptibly within a human lifetime. Below the mantle lies the outer core, extending from about 2,900 to 5,150 kilometers beneath the surface. The outer core is composed primarily of molten iron and nickel. Unlike the solid mantle above it, the outer core is liquid. The movement of molten metal in this region generates Earth's magnetic field through a process known as the geodynamo. The magnetic field extends far into space, forming the magnetosphere. This invisible shield deflects charged particles from the sun, protecting the atmosphere and surface from harmful radiation. At the very center of Earth lies the inner core. It has a radius of about 1,220 kilometers and is composed mainly of iron and nickel. Despite extremely high temperatures, comparable to the surface of the sun, the inner core remains solid due to immense pressure. The pressure at Earth's center is more than 3 million times greater than atmospheric pressure at sea level. Heat within Earth originates from two primary sources: residual heat from planetary formation and radioactive decay of elements such as uranium, thorium, and potassium. This internal heat drives mantle convection, fuels volcanic activity, and maintains the liquid state of the outer core. Volcanoes serve as outlets for internal heat. When magma rises through the crust and reaches the surface, it releases energy stored deep within the planet. Over geological timescales, volcanic outgassing contributed to the formation of Earth's early atmosphere. Earth's layered structure is a product of differentiation. During the planet's early molten phase, heavier elements such as iron sank toward the center, while lighter silicate materials rose toward the surface. Gravity organized the planet into layers. Today, this layered structure maintains stability. The solid crust supports life. The flowing mantle drives plate motion. The molten outer core generates the magnetic field. The solid inner core anchors the planet's center. These systems operate continuously and slowly. Earth's interior is dynamic, but not chaotic. Movement occurs over millions of years. Heat transfers gradually. Plates shift steadily. From the surface, much of this activity remains unseen. Yet beneath every landscape, beneath every ocean, beneath every city, the planet's internal processes continue in calm, measurable cycles. Earth is not static. It is a layered, evolving system, shaped by gravity and heat. And tonight, as you rest on its surface, the planet's interior continues its slow and steady motion. Stable, balanced, and enduring across deep time. The biosphere is the global system that includes all living organisms and the environments in which they interact. It extends from the deepest ocean trenches to the upper layers of the atmosphere, where microscopic life can still survive. Although Earth is vast, the region that supports life is relatively thin. Most life exists within a narrow zone that includes the lower atmosphere, the surface, and the upper layers of soil and ocean. This delicate layer is sustained by energy from the sun and by the cycling of essential elements. Life on Earth depends on a continuous flow of energy. Nearly all ecosystems derive their energy from sunlight through the process of photosynthesis. Plants, algae, and certain bacteria convert sunlight, carbon dioxide, and water into glucose and oxygen. This process forms the foundation of most food chains. The oxygen released during photosynthesis accumulates in the atmosphere and supports respiration in animals and many microorganisms. Through respiration, organisms convert oxygen and organic molecules into energy, releasing carbon dioxide as a byproduct. This exchange between photosynthesis and respiration forms part of the carbon cycle. Carbon moves through the atmosphere, oceans, soil, rocks, and living organisms. Over short timescales, it circulates through ecosystems. Over geological timescales, it becomes stored in sedimentary rocks and fossil fuels. The water cycle is another essential system within the biosphere. Water evaporates from oceans and land surfaces, condenses into clouds, and returns as precipitation. This continuous movement distributes fresh water across continents and sustains rivers, lakes, forests, and agricultural systems. Nitrogen, an essential component of proteins and DNA, circulates through the nitrogen cycle. Although nitrogen gas makes up about 78% of Earth's atmosphere, most organisms cannot use it directly. Specialized bacteria convert atmospheric nitrogen into forms that plants can absorb. Animals obtain nitrogen by consuming plants or other animals. These interconnected cycles demonstrate that Earth's biosphere operates as a system of balance and exchange. Life exists in a wide range of environments. Tropical rainforests contain some of the highest biodiversity on the planet, with complex ecosystems structured in vertical layers. Coral reefs, often called the rainforests of the sea, support immense marine diversity within relatively small areas. In contrast, deserts and polar regions support fewer species. Yet even these environments host organisms adapted to extreme conditions. Microbial life has been found in deep-sea hydrothermal vents, Antarctic ice, and beneath Earth's crust. The resilience of life arises from adaptation and evolution. Through natural selection, populations gradually change over generations in response to environmental pressures. Over billions of years, this process has produced the diversity of species present today. Earth is estimated to host millions of species, though only a fraction have been formally described by scientists. Each species occupies a specific ecological niche, a role within its ecosystem that includes how it obtains energy, interacts with other organisms, and contributes to nutrient cycles. Biodiversity enhances ecosystem stability. Diverse systems are often more resilient to disturbances because multiple species can perform similar ecological roles. The biosphere also interacts with the atmosphere and oceans in regulating climate. Forests absorb carbon dioxide and release oxygen. Phytoplankton in oceans contributes significantly to global oxygen production. Wetlands filter water and moderate flooding. These interactions illustrate that Earth's living systems are not separate from physical systems. They are integrated components of a single planetary process. From space, the biosphere appears subtle. Thin green and blue patterns across continents and oceans. Yet within that thin layer exists extraordinary complexity. Life emerged on Earth at least 3.5 billion years ago. Since then, it has transformed the atmosphere, influenced climate, and shaped geological processes. The presence of liquid water, moderate temperatures, and a stable atmosphere has allowed life to persist and diversify. These conditions are not guaranteed on other worlds. The biosphere is dynamic, but gradual in its long-term changes. Forests grow over decades. Coral reefs build over centuries. Evolution unfolds over millions of years. The balance of life on Earth is maintained through feedback mechanisms, energy flows, and cycles of matter. Although local environments change, the broader system operates through stable physical and biological principles. The biosphere represents the living surface of a rotating planet. It depends on sunlight, gravity, atmospheric chemistry, and ocean circulation. Together, these systems create a world where life can exist, adapt, and continue. Earth's biosphere is not separate from the planet's structure or climate. It is woven into them, a continuous interaction between rock, water, air, and living organisms. And through this balance, life endures. Earth's climate is the long-term pattern of temperature, precipitation, and atmospheric conditions across the planet. Unlike daily weather, which can change rapidly, climate operates over decades, centuries, and geological timescales. The stability of Earth's climate is the result of interactions among the atmosphere, oceans, land surfaces, ice sheets, and the biosphere. These components exchange energy and matter continuously, forming a complex but measurable system. The primary source of Earth's climate energy is the sun. Solar radiation reaches the planet unevenly. The equatorial regions receive more direct sunlight, while the poles receive less. This uneven heating drives atmospheric and oceanic circulation, redistributing thermal energy across the globe. A portion of incoming solar radiation is reflected back into space. Ice, snow, and clouds are particularly reflective. This reflectivity is known as albedo. Surfaces with high albedo help regulate planetary temperature by limiting heat absorption. The remaining solar energy is absorbed by oceans, land, and atmosphere. Earth then emits energy back into space as infrared radiation. The balance between incoming solar radiation and outgoing heat determines the planet's average temperature. Certain gases in the atmosphere, including carbon dioxide, methane, and water vapor, absorb and re-emit infrared radiation. This natural process, known as the greenhouse effect, helps maintain Earth's average surface temperature at approximately 15 degrees Celsius, 59 degrees Fahrenheit. Without the greenhouse effect, Earth's average temperature would be far below freezing, and liquid water would be rare. The greenhouse effect is therefore essential to sustaining life. Over geological timescales, Earth's climate has experienced natural variations. Ice ages, for example, have occurred periodically over the past several million years. During glacial periods, large ice sheets covered significant portions of continents. These cycles are influenced by variations in Earth's orbit and axial tilt, known collectively as Milankovitch cycles. Changes in orbital shape, tilt angle, and precession alter the distribution of solar energy received by Earth, affecting long-term climate patterns. Volcanic activity can also influence climate. Large eruptions release ash and sulfur compounds into the atmosphere, temporarily reflecting sunlight and causing short-term cooling. Oceans play a central role in climate regulation. They absorb vast amounts of heat and carbon dioxide. Deep ocean currents redistribute thermal energy over centuries. This slow circulation contributes to long-term stability. Ice sheets and glaciers also influence climate through feedback mechanisms. When ice expands, it increases albedo, reflecting more sunlight and reinforcing cooling. When ice melts, darker surfaces absorb more heat, promoting warming. Earth's climate system contains both stabilizing and amplifying feedbacks. Stabilizing feedbacks help maintain equilibrium, while amplifying feedbacks can intensify change under certain conditions. Despite periodic shifts, Earth has maintained conditions suitable for liquid water for billions of years. This long-term habitability is unusual among known planetary bodies. The interaction between climate and life has also shaped Earth's history. Early photosynthetic organisms altered atmospheric composition by increasing oxygen levels. Vegetation influences carbon storage and surface reflectivity. Climate operates across multiple timescales. Daily temperature fluctuations, seasonal cycles, and multi-century oscillations all exist within a broader planetary framework. Measured from space, Earth's climate appears dynamic but organized. Cloud systems form predictable patterns. Ocean currents follow established paths. Polar ice expands and contracts seasonally. The planet maintains energy balance through continuous exchange between atmosphere, oceans, land, and ice. Although climate varies, it does so according to physical principles governed by radiation, thermodynamics, and fluid dynamics. Earth's long-term stability arises not from stillness, but from steady interaction. Energy flows inward from the sun. Heat flows outward into space. Oceans circulate slowly. Ice forms and melts. Atmospheric gases absorb and emit radiation. Through these balanced processes, Earth remains within a range that allows life to exist. The climate system is neither static nor chaotic. It is regulated by measurable forces and gradual cycles. And across deep time, despite change and variation, Earth continues to orbit the Sun in relative equilibrium, a rotating planet maintaining its temperature through the quiet laws of physics. Earth is the third planet from the Sun and the fifth largest in the solar system. It orbits at an average distance of approximately 149.6 million kilometers, a distance known as 1 astronomical unit, AU. This position places Earth within the Sun's habitable zone, where temperatures allow liquid water to exist on the surface. The solar system formed about 4.6 billion years ago from a rotating cloud of gas and dust known as the solar nebula. As gravity caused material to collapse inward, the Sun formed at the center. Remaining particles gradually collided and combined to form planets, moons, asteroids, and comets. Earth formed through a process called accretion. Small, rocky bodies merged over millions of years, generating heat from impacts and radioactive decay. Early in its history, Earth experienced frequent collisions, including a significant impact with a Mars-sized body, often referred to as Theia. This event is widely accepted as the origin of the Moon. The Moon orbits Earth at an average distance of about 384,400 kilometers. It plays a stabilizing role in Earth's axial tilt. Without the Moon, Earth's rotation axis might vary more dramatically over time, leading to more extreme climate fluctuations. Earth's orbit is slightly elliptical, but nearly circular. It completes one revolution around the Sun every 365.25 days. The additional quarter day is accounted for by adding a leap day approximately every 4 years. Earth rotates on its axis once every 24 hours, creating the cycle of day and night. The axis is tilted approximately 23.5 degrees relative to its orbital plane. This tilt produces seasonal variations in sunlight distribution across the planet. Compared to other planets in the solar system, Earth possesses several distinguishing characteristics. It has abundant surface liquid water, a nitrogen-oxygen atmosphere, active plate tectonics, and a magnetic field generated by its molten outer core. The inner planets, Mercury, Venus, Earth, and Mars, are rocky and relatively small. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants composed largely of hydrogen, helium, and other volatiles. Earth's size and mass allow it to retain a substantial atmosphere while avoiding excessive gravitational compression. Mercury, being smaller, cannot retain a thick atmosphere. Venus, similar in size to Earth, developed a dense carbon dioxide atmosphere that traps heat efficiently, leading to extreme surface temperatures. Mars, smaller and farther from the Sun, has a thin atmosphere and cold surface conditions. While evidence suggests that liquid water once flowed on Mars, present conditions are largely arid and frozen. Earth's magnetic field distinguishes it further. Generated by convection in the liquid outer core, the magnetosphere shields the planet from solar wind. Charged particles from the Sun are deflected, protecting the atmosphere from erosion. The solar system itself orbits the center of the Milky Way galaxy at a velocity of about 828,000 kilometers per hour. One full galactic orbit takes approximately 225 to 250 million years. Within this broader cosmic framework, Earth occupies a stable orbit, influenced primarily by the Sun's gravity. The gravitational interactions among planets produce minor variations, but do not significantly disrupt Earth's path. Asteroids and comets occasionally cross Earth's orbital region. Most burn up upon entering the atmosphere due to friction and heat. Larger impacts are rare, but have influenced Earth's geological and biological history. The solar system exists within a region of the Milky Way known as the Orion Arm. This location is relatively distant from the galactic center, where radiation levels are higher. Earth's position within both the solar system and the galaxy contributes to its long-term stability. From a cosmic perspective, Earth is one planet among many, orbiting one star among billions. Yet, its combination of orbital distance, mass, atmosphere, water, and geological activity has produced conditions suitable for life for billions of years. Earth's place in the solar system is defined by motion, balance, and gravitational interaction. It rotates steadily. It orbits consistently. It remains aligned within a structured planetary system. And within that system, Earth continues its path. A stable world moving predictably through space under the steady influence of gravity and solar energy. Earth's rotation is one of the most fundamental motions governing life on the planet. The planet rotates around its axis once approximately every 24 hours. This rotation creates the cycle of day and night and establishes the basis for the measurement of time. Earth rotates from west to east. As a result, the Sun appears to rise in the east and set in the west. At the equator, the surface moves at a speed of roughly 1,670 kilometers per hour due to this rotation. Despite this high velocity, humans do not perceive motion because everything on Earth moves together at the same constant rate. The axis of rotation is an imaginary line running through the north and south poles. This axis is tilted approximately 23.5 degrees relative to the plane of Earth's orbit around the Sun. The tilt is responsible for seasonal variations in sunlight intensity and day length. As Earth orbits the Sun over the course of a year, different regions receive varying amounts of solar energy. When the northern hemisphere tilts toward the Sun, it experiences longer days and warmer temperatures. At the same time, the southern hemisphere tilts away and experiences shorter days and cooler conditions. 6 months later, the situation reverses. The points at which day and night are approximately equal in length worldwide are known as equinoxes. The points at which one hemisphere receives its maximum tilt toward or away from the Sun are known as solstices. Earth's rotation is not perfectly constant. Over long timescales, tidal interactions with the Moon gradually slow the planet's rotation. Each century, the length of a day increases by approximately 1.7 milliseconds. This deceleration occurs because tidal friction transfers rotational energy from Earth to the Moon, causing the Moon to slowly move farther away. Timekeeping systems are based on Earth's rotation and orbit. A solar day represents one full rotation relative to the Sun. A sidereal day, slightly shorter, measures one rotation relative to distant stars. A year represents one full orbit around the Sun. Human civilizations have historically organized calendars around these natural cycles. Lunar calendars track the phases of the Moon, while solar calendars follow Earth's orbit. Modern timekeeping incorporates atomic clocks to maintain precision, occasionally adding leap seconds to account for slight variations in Earth's rotation. Beyond daily and yearly cycles, Earth experiences additional long-term variations. Axial precession, a slow wobble of Earth's rotation axis, occurs over approximately 26,000 years. This motion gradually shifts the position of the celestial poles and alters the timing of seasons relative to Earth's orbital position. Obliquity, or the angle of Earth's tilt, also varies slightly over tens of thousands of years. These gradual changes influence long-term climate patterns and contribute to ice age cycles. Earth's rotation also affects atmospheric and oceanic circulation. The Coriolis effect, resulting from rotational motion, deflects moving air and water currents. This deflection shapes trade winds, jet streams, and large-scale weather systems. At the equator, centrifugal force slightly counteracts gravity due to rotation. This effect causes Earth to bulge at the equator and flatten slightly at the poles. The equatorial diameter is approximately 43 kilometers larger than the polar diameter. Day and night regulate biological rhythms. Many organisms follow circadian cycles synchronized with Earth's rotation. These internal clocks influence sleep patterns, hormone production, metabolism, and behavior. Seasonal cycles influence migration, flowering, reproduction, and food availability across ecosystems. The predictable nature of Earth's rotation and orbit allows life to adapt to recurring environmental patterns. Despite continuous motion, Earth's rotation is stable and orderly. It does not fluctuate abruptly. The transition from day to night is gradual, marked by twilight. The progression of seasons unfolds predictably. The planet turns steadily, maintaining temporal structure for all life upon it. Time on Earth is not imposed externally. It arises directly from motion, rotation, orbit, and gravitational interaction. Each sunrise, each sunset, each passing season is the result of planetary dynamics operating according to physical law. Earth rotates. The Sun appears to move across the sky. The Moon advances through phases. And through these quiet cycles, time flows steadily on a planet moving calmly through space. Earth is surrounded by an invisible magnetic field that extends far into space. This magnetic field, known as the magnetosphere, plays a crucial role in protecting the planet from solar radiation and charged particles emitted by the Sun. The magnetic field is generated deep within Earth's outer core. The outer core is composed primarily of molten iron and nickel. As this electrically conductive fluid moves due to convection and planetary rotation, it generates electric currents. These currents produce a magnetic field through a process called the geodynamo. The magnetic field resembles that of a bar magnet, with magnetic north and south poles. However, unlike a simple magnet, Earth's magnetic field is dynamic and constantly changing in strength and orientation. The magnetosphere forms a protective boundary around Earth. When solar wind, a stream of charged particles from the Sun, approaches the planet, the magnetic field deflects most of these particles. Without this shield, high-energy radiation could gradually erode the atmosphere and increase surface radiation levels. The interaction between solar wind and the magnetosphere compresses the field on the side facing the Sun and stretches it into a long tail on the opposite side. This tail can extend millions of kilometers into space. At certain points near the magnetic poles, some charged particles follow magnetic field lines downward into the upper atmosphere. When these particles collide with atmospheric gases, they release energy in the form of light. This phenomenon produces the auroras, the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. Auroras appear as shifting curtains or arcs of green, red, or purple light. Their colors depend on which atmospheric gases are excited and at what altitude. Oxygen typically produces green and red light, while nitrogen can produce blue or violet hues. Earth's magnetic poles are not fixed. They drift gradually over time. In addition, geological records indicate that Earth's magnetic field has reversed many times in the past. During a reversal, magnetic north and south exchange positions. These reversals occur irregularly, separated by hundreds of thousands to millions of years. Despite reversals and gradual shifts, the magnetic field has persisted for billions of years. Its presence has contributed significantly to the long-term retention of Earth's atmosphere. The magnetic field also influences navigation. Many animals, including birds, sea turtles, and certain bacteria, appear to use Earth's magnetic field as a guide during migration. Humans have relied on magnetic compasses for centuries to determine direction. Earth's atmosphere itself provides additional protection. The ozone layer in the stratosphere absorbs much of the sun's ultraviolet radiation. Together, the magnetosphere and atmosphere create a layered defense system. Beyond protection, the magnetosphere is part of a broader system of solar-terrestrial interaction. Solar activity varies over approximately 11-year cycles. During periods of heightened solar activity, solar flares and coronal mass ejections can intensify interactions with Earth's magnetic field. These events may temporarily disrupt satellite communications or power grids. However, Earth's magnetic field absorbs and redistributes much of this energy, maintaining overall planetary stability. Measured from space, the magnetosphere appears as a dynamic structure shaped by solar wind. Invisible to the eye, it remains essential to the continuity of life. Earth is not exposed directly to space without defense. It is encircled by electromagnetic protection generated from within its own core. The molten iron beneath the surface moves steadily. Electric currents form naturally. Magnetic lines extend outward. The result is a quiet shield, persistent, unseen, and constant. This invisible system operates continuously without human awareness. It does not produce sound or visible motion under ordinary conditions. Yet it surrounds the planet at every moment. The magnetic field represents another example of Earth's internal processes supporting surface stability. Deep within the planet, motion generates protection. In space, invisible forces deflect radiation. In the sky, auroras glow as evidence of interaction. Through these processes, Earth remains shielded as it travels through a dynamic solar system. And while the sun emits energy across space, Earth's magnetic field quietly ensures that the planet remains protected, balanced, and capable of sustaining life. Earth's history spans approximately 4.54 billion years. This immense duration is divided into structured intervals known as eons, eras, periods, and epochs. Together, these divisions form the geologic timescale, a framework used by scientists to understand the planet's long-term development. The earliest eon, the Hadean, began with Earth's formation. During this time, the surface was extremely hot, and frequent impacts from space were common. Gradually, as the planet cooled, the first stable crust formed. The Archean eon followed, beginning around 4 billion years ago. During this period, the first evidence of life appeared in the form of simple microorganisms. These early life forms lived in oceans and likely relied on chemical energy before photosynthesis became widespread. The Proterozoic eon, lasting from about 2.5 billion to 541 million years ago, saw significant changes in atmospheric composition. Photosynthetic organisms released oxygen into the atmosphere in what is known as the Great Oxidation Event. This transformation allowed more complex life to evolve. The current eon, the Phanerozoic, began approximately 541 million years ago. It is divided into three major eras: the Paleozoic, Mesozoic, and Cenozoic. The Paleozoic era was marked by the rapid diversification of life in the oceans, known as the Cambrian explosion. Over time, plants and animals colonized land. The era ended with the largest mass extinction in Earth's history, eliminating a significant portion of marine and terrestrial species. The Mesozoic era, often called the Age of Reptiles, included the time when dinosaurs dominated terrestrial ecosystems. During this era, continents gradually separated as tectonic plates shifted. The Mesozoic concluded with another mass extinction event, approximately 66 million years ago. The Cenozoic era, which continues today, is characterized by the diversification of mammals and birds. During this time, continents moved toward their present positions. Mountain ranges, such as the Himalayas, formed through plate collisions. Throughout geological time, Earth's surface has undergone constant change. Continents have merged into supercontinents and later fragmented. One well-known supercontinent, Pangaea, existed approximately 335 to 175 million years ago before breaking apart. Mountain formation, known as orogeny, occurs when tectonic plates converge. Erosion gradually reshapes these mountains, transporting sediment into oceans, where it forms new rock layers. Rocks record Earth's history. Igneous rocks form from cooled magma. Sedimentary rocks form from accumulated particles compressed over time. Metamorphic rocks result from pressure and heat altering existing rock. By studying rock layers and fossil evidence, scientists reconstruct ancient climates, ocean conditions, and biological evolution. Fossils reveal the progression of life from simple marine organisms to complex terrestrial ecosystems. Geological processes operate on timescales far beyond human experience. Erosion may lower mountains by millimeters per year. Tectonic plates drift only centimeters annually. Yet over millions of years, these gradual movements reshape continents and oceans. Mass extinctions have occurred periodically in Earth's history. These events, caused by volcanic activity, climate shifts, or asteroid impacts, reduced biodiversity significantly. However, life has repeatedly recovered and diversified. Earth's internal heat continues to drive tectonic motion and volcanic activity. These processes recycle materials between the surface and interior, maintaining long-term planetary activity. The rock cycle, like other Earth systems, is continuous. Rocks form, erode, transform, and reform in repeating patterns. Geological time illustrates that Earth is dynamic rather than static. Landscapes that appear permanent are temporary on a planetary scale. Oceans open and close. Mountains rise and erode. Continents shift gradually. Despite these changes, Earth has maintained conditions suitable for life for billions of years. The deep history of Earth demonstrates both transformation and continuity. While environments and species evolve, the fundamental physical processes, gravity, heat transfer, plate motion, persist. Geologic time reveals a planet shaped by slow, steady forces operating across immense spans. Earth's present surface is only a moment within a much longer narrative. And beneath today's landscapes, the processes of deep time continue, gradual, measurable, and enduring across billions of years. Earth's atmosphere is a thin envelope of gases surrounding the planet, held in place by gravity. Although it extends thousands of kilometers into space, most of its mass is concentrated within the first 30 kilometers above the surface. The atmosphere is composed primarily of nitrogen, approximately 78%, and oxygen, approximately 21%. The remaining 1% consists of argon, carbon dioxide, neon, helium, methane, and trace gases. Water vapor is also present in varying amounts, depending on location and weather conditions. The atmosphere is divided into several layers based on temperature changes with altitude. The lowest layer is the troposphere, extending from the surface to an average height of about 8 to 15 kilometers. This is the layer in which weather occurs. Clouds form here, winds circulate, and temperature generally decreases with altitude. The troposphere contains approximately 75% of the atmosphere's mass and nearly all of its water vapor. Because it is closest to the surface, it directly influences climate and living organisms. Above the troposphere lies the stratosphere, extending up to about 50 kilometers. In this layer, temperature increases with altitude due to the presence of the ozone layer. Ozone absorbs much of the sun's ultraviolet radiation, converting it into heat. The ozone layer plays a crucial protective role. Without it, harmful ultraviolet radiation would reach Earth's surface in greater quantities, affecting ecosystems and increasing biological risk. Above the stratosphere is the mesosphere, extending to approximately 85 kilometers. In this layer, temperatures decrease again with altitude. The mesosphere is where most meteoroids burn up upon entering Earth's atmosphere, producing visible streaks of light known as meteors. The next layer, the thermosphere, extends from about 85 kilometers to several hundred kilometers above Earth. Temperatures in the thermosphere increase significantly with altitude due to absorption of high-energy solar radiation. The thermosphere contains the ionosphere, a region of charged particles that reflects and modifies radio waves. This layer enables long-distance radio communication by allowing signals to travel beyond the horizon. The outermost layer, known as the exosphere, gradually transitions into space. In this region, gas molecules are sparse and may travel long distances before colliding with one another. Although the atmosphere appears invisible from the surface, it performs multiple essential functions. It regulates temperature by distributing heat through circulation patterns. It protects against solar radiation and small meteoroids. It supports respiration and photosynthesis. It enables the water cycle. The atmosphere also contributes to the greenhouse effect, which maintains Earth's average temperature. Water vapor, carbon dioxide, and other greenhouse gases absorb infrared radiation emitted by the surface and re-radiate it, preventing excessive heat loss. Air pressure decreases with altitude. At sea level, atmospheric pressure supports liquid water and allows oxygen exchange in the lungs. At higher elevations, reduced pressure leads to lower oxygen availability. Atmospheric circulation arises from differences in temperature and pressure. Warm air rises near the equator, while cooler air sinks near the poles. This movement forms large-scale circulation cells that help distribute energy globally. Jet streams, narrow bands of fast-moving air, form near the boundaries of atmospheric layers. These high-altitude winds influence weather systems and seasonal patterns. The atmosphere is not static. It is dynamic and continuously mixing. Gases circulate around the planet over timescales of weeks to months. Despite its thinness relative to Earth's size, the atmosphere maintains stability through gravitational containment and thermal balance. Viewed from space, The atmosphere appears as a faint blue line along Earth's curved horizon. This thin band supports all terrestrial life. Without the atmosphere, Earth's surface would experience extreme temperature differences between day and night. Liquid water would evaporate more rapidly, and harmful radiation would reach the ground unfiltered. The atmosphere represents a balance between gravitational force, solar energy, and chemical composition. It is neither solid nor fixed, but fluid and responsive. Air moves quietly. Clouds form and dissipate. Pressure systems shift gradually. Through these continuous processes, Earth's atmosphere sustains a stable environment suitable for life. And above the surface, layer by layer, the air grows thinner until it merges seamlessly with the surrounding space. A delicate yet enduring shield surrounding a rotating planet.